this is class 13, and we're going to introduce stress concentration. It's a relatively short lecture, I think. I don't know. Can't recall. I think so. So the big idea is that when there's a discontinuity in a piece, let's say, for instance, I want to take this piece of paper. Right, now first off, it doesn't have a discontinuity into it, right? And I pull on the paper, and we're fine. But now I take a little tear into there. Now it's discontinuous, and I pull on it. I'm gonna have to cheat. I pull on it, and it can break, right? So the discontinuity has sort of like a amplifying effect onto the stress. It amplifies it because it's not continuous discontinuity. The simplest one is a hole in a plate. And now the plate's going to be weaker because there's less material there, but in addition to that, there's like a disruption in the we can think of it as the flow of the stress, and that's we can call it a stress riser, and it increases, it amplifies the stress. So there's a theoretical amount that it does. That theoretical also shows up in finite element analysis, interestingly enough. So that's what the T stands for. So we could say that we have a stress concentration is really this ratio, and there's a capital K, of the maximum stress divided by the nominal stress. Like, what's the nominal stress? Well, that's a really good question. You really need to look into the captions of each of the figures, and they will give you what they consider the nominal stress. Well, if you take a look at this equation right here, right, especially this guy right there, it's really just the meat that's left over right there. Let me go switch over to this right here. Oops. Don't get dizzy. That's really this right here. So if we were to look at a cross section, oops, I did a bad job of my cross section. I made too many videos today, and now I'm tired. Okay, so there you go. Here's our cross section, and there you go, like that right there. We could see that the area that we're trying to get is going to be W, which is the width of this, minus this, right? So that's just this and that length, right? Add those two together right there. We've really just taken the total W, subtracted out the D, and then multiplied it by the thickness. So yeah, that makes sense that that's going to be the nominal area. So we get the nominal stress by dividing the force by the nominal area. So we can just look in these captions anytime we want to try to figure out what this thing is based on. So if you want to find the stress, the maximum stress, what you do is you find the ratio here of the diameter of the hole to the width. And let's say that it's like 0.3. Let's say the width is, the diameter is only 0.3 times the width that we get right there. We're going to predict it's going to have like something like 2.3 and change, right? Remember, it's weird because there's 2.2 and 2.4 right there. So you have to be careful that notably that 2.3 is somewhere in there. So call it like 2.35. And we want to do a little bit of we want to do a pretty good job of estimating how far that is in there. In fact, it actually looks like it's more than 2.35. 2.35. I'd say 2.36. Kind of have to make a guess. And so I asked the question, why does this happen? And I don't have my notes out. I'm going to see what I said. Let me see what I said when I wrote the notes last time. Why does this happen? Well, it's not in this book. It's in a different book. And I don't remember what I wrote. Okay. Remember what stress is, right? What is stress? Stress is the distribution of internal loads. Well, axial stress, in this case, is usually uniform. But now it can't be uniform because it was uniform over here. It was uniform over here, far away from this, but now it's been disrupted. So the distribution of internal loads is not uniform anymore because there's been a disturbance in that uniform distribution. So it ends up getting larger, closer to where that disruption is. And so that's the location, like right here near the center of the hole that we're going to find. So we have a disruption in the distribution of internal loads. And the best analogy, I think, for this is like a fluid flow, like a rock in a stream and like turbulence around it. That's the one that comes to my mind right here. So you could see these little streamlines. If you've taken fluid mechanics, you might be familiar with them. Or another disruption is this fillet. You can see that we come from a wide thing down to a narrow thing. Now the stress is going to be higher here than it was here because there's less area here, but that transition between the two is disrupted. So here's a reference here that describes this more, but that's the best analogy that I can think of. And we talk about other names for stress concentration. Well, I said, what did I say? Sorry. I called it sometimes a stress riser. It's due to a discontinuity, but I call this, sometimes it's called a stress riser, this discontinuity, or I often will refer to as hot spots. And we will find this a lot in finite element analysis, and we can confirm it with finite element analysis, which is a good use of it. But we also want to be aware that there's a certain amount. Let's see if I'm going to say this correctly, or when I want to say this. Let's see. Okay, so we actually will see this in an upcoming page in the book here. But let me talk about this stuff we should know about stress concentrations. There you go. That's what I want to say. First of all, it's a localized stress. And we can find these factors for different scenarios in Appendix A15 and A16. And these are common ones, but there's way more. And this dude, Peterson, literally wrote the book, or books and books, about stress concentration. And he did this like in the 1950s. And the way that he did it, it's sort of interesting. You could look it up. He took this special plastic, plexiglass stuff, and he made the different shapes out of them, cut them out, and puts loads onto them. And these things went under the right lighting, actually showed like these kind of like little plots, these little lines to kind of show where this is. So he went backwards and came up with all these curves. And it wasn't until we could really use FEA, this was in the 50s, so like maybe you got in the 60s and the 70s where it's easy enough to just replicate this accurately. And he's spot on. It was pretty amazing. I'd like to find like a documentary on this or something along those lines. It'd be pretty interesting, I think. I want to find like a video maybe of that in action. And I wonder if I could find it like really quickly. Let's see. Videos on this, but I did find a paper that might have been the seminal paper, because it was this says, according to, at least from Google Scholar, it says it should be 1930, but I see some of the references in this are from later, from 1933, so I'm not quite sure what you have here, but we have a wall and someone who I can't pronounce his last name, but they're from East Pittsburgh, Pennsylvania, and they're showing these notches. So these predate Peterson's work, which, by the way, if you just do Peterson's stress concentration, if you just go right here, you'll see Peterson's stress concentration, a book full of them, I think. I don't know. I might accidentally have just downloaded a book. Here you go. You could actually find this book. Probably shouldn't be able to find this book, but you can, and you can get. I think I saw that it was dedicated to his mother. That was weird. I just saw that and it flashed by. But anyway, you'll find he's got equations in here, but at some point you're going to find a whole bunch of these different figures. He's going to make a liar out of me, isn't he? All right. So I don't know where. I don't want to waste too much time doing this. Let me get. Yeah. There you go. Boom. No, come on. Where are all your figures? Wouldn't you know? Come on, just show me some figures. Anyway, you could find him, right? So Peterson is out there. Where what's the foot lost? There you go. There you go. There's a Peterson. You can find Peterson's stress concentration. Peterson's is the big name. But we could go back to here and you could see pictures of what he did to get these, which is pretty amazing. He used the photoelasticity effect in order to find these stress concentrations. And here's like this little rig, and they're putting light through it, and they're trying to get like stress concentration factor from this. All right, so this is where this comes from, right here. But amazingly, it was done years and years ago before FEA. So let's take a look at some other things. Okay, so here's other information I wanted to talk about. It's a good idea that we can look for trends of what's taking place. You could see what parameters is it really dependent on, and so the first one we've just seen is just been a hole in a plate, but we'll see in a second. There's many of them. So when should we use these stress concentrations? Well, it turns out that we don't really need to use them for ductile materials. So, well, why is that? Well, these stresses might be real, but they don't cause the kind of failure that we might think, because when it's ductile materials, that's going to be a local failure. And what ends up happening is that's going to be like a really small little area, might get to the yielding strength region, we get beyond the yield strength. But that actually strain hardens that piece and makes it kind of a little stronger, really locally. And then the next guy to it, he kind of takes over for it. So what it turns out is we don't really get the kind of failures that you'd expect from, based on yield strength at least, when you have that high stress concentration on a ductile material. It's only brittle materials that really will fail this way. And we'll also see that we're going to take some, and we're going to see that we have fatigue on ductile materials. We'll use this stress concentration, but we'll actually reduce it down some with something called notch sensitivity. So that's something that's coming up in fatigue. So, but this is a stress riser, and we will see, we'll see high stresses in local spots where there's a discontinuity in an FEA. So here was a tour through some of the ones in Shigley. So here is the one that we just saw, and interestingly enough, there you go, we saw the source from this too, which is kind of neat, right? We can kind of see here is, and you see it comes up to right around 3 right there. So that's kind of neat that we could see this, and we can see it comes up to 3. So 3 times the nominal stress is what happens right here at these corners. Here's one where we have a bending about a plate with a hole, and you can see that we have the ratio now is going to be the thick, here you go, a D over H right here, D over H, right? So the thickness actually matters. So we find, and we got to be careful because we might have to interpolate, like if it was under like 0.375 was that ratio, we might have to draw a line in between the 0.25 and the 0.5. And then we also see that it's a function of that D and W, just like the other one was. So we would see where they would cross, maybe, let's say if it was 0.2, and we would find out that's when. And of course, but this is the load, right? And this is the nominal stress, right? The nominal stress is going to be based on this moment of inertia, right? So keep that in mind. Got to look at the caption. Here's one where we have a notch, and this notch, this is going to be a function of W over D, right? So this width compared to these, we call this the throat areas, right, to the bottom of this, and it's also a function of the radius of this to the throat, right there. And so you want to note that we take the area is going to be that throat times the thickness, and that's the nominal stress. Here's one, there's a fillet where we make this transition from a wider thing, for whatever reason we call it D. I don't think the big D and little d, I never think that makes sense. I'd go big W, little w, they're widths, but just got to be careful with the naming of these things. And you could see that we have the D over D ratios. They only goes up to 1.5, unfortunately. I'd like to see other curves. So sometimes we'll see that we actually have to use this 1.5 when we don't know anything more. So we don't try to extrapolate. We will interpolate, but we won't extrapolate for the curves. But we see this D over D ratio. We do see that the stress, the nominal stress, is based on the smaller of the two widths right here times the thickness. And here's one where we have torsion, right? Now we have this round piece, and there's a fillet in between in this transition. And here again we have a D over D, but now these are diameters, but you can see that we have the fillet radius right there. It kind of matters, and it's the smaller of the two shafts that's going to determine that J. For whatever reason, is they C for some reason. I don't know why. It's R, but I guess because they didn't want to use this R, right? So what they mean is they call that C right there, that dimension. So this was in torsion, and this is in bending. And this comes up in shaft design, right? When we have shaft and there's a step in the shaft with two different diameters for the step, so that'll matter to us. So here's my FEA confirmation. And the following examples, which I'll probably record tomorrow, so I'll wear a different shirt because I'm going to go home and eat some dinner here now. But here's I ran some FEA on that simple one where we just have a plate, right, with a hole in it in tension, and I just made the hole bigger. So I'll put 100 pounds onto the thing. I made the width of it is 5, the thickness is 1. So the hole, I've picked a D over W of 0.1 on purpose. So I have a hole diameter of 0.5. So I find the maximum stress is 61.93. That's this actually says 63.36, so it's sort of cheating. But I think what I actually did is I took the average through the thickness. I think that's what I did, instead of taking the maximum. But this one is calling out 63.36. The nominal is 22.22. So what I find, I get a 2.78. Similarly, now I went to a D over W of 0.2. Right, so but take a flip back and forth between them. You can kind of see that size. But we want to take a look at the distribution, right? The color distribution. Red, the transition between like red and more red is 90 and 100. So you can see right here. So this is a this actually has a higher one. Yeah, it actually has a higher stress, but the nominal stress is also higher, right? So that ratio now goes 2.566. So I went 2.787, 2.566. So I make the hole bigger, and I get this 2.394. A hole bigger, 2.273. Right, here's the 0.4, and here's the 0.5. Right, so you see 2.195. Here's 0.6. And you can see where you can see the stress is largest right there. It really shows up on this one. And here's my 0.7, and here's 0.8, and you can see here's my 2.086. And so here's the data points from the ones that I just showed, that confirming my trend, right? I could probably have been very more meticulous in this. I could experiment with the thickness, because you don't see the thickness causing, but it does matter how you can make it like really thick, and then what number to use. But you can see what the trend is, and that it's going along. So it's a pretty interesting thing to do with FEA. To make this comparison, it does give you sort of like a feel for the effect of making transitions from one thing to another. It's also a cautionary tale, because we might like pick out the maximum number in something, but it's just because we made like a hard jag in the thing. So we will do some other examples, but I'm going to go home and eat some dinner because it's Wednesday and I want to eat dinner with my wife. Ta-da! 20-minute video.